A lot of pop science outlets give a certain summary of quantum computing that I can almost guarantee leads to misconceptions. The summary goes something like this. In a classical computer, data is stored with bits, some sequence of ones and zeros, but in a quantum computer, you are able to represent every possible sequence of bits of some fixed length all at once, in one big thing known as a superposition. And sometimes the implication of these summaries is that quantum computers can be faster by basically doing whatever a classical computer would do, but to all of these sequences in parallel. Now, this does gesture at something that's kind of true, but let me see if I can prove to you why I think this leads to misconceptions, and I'll prove it using a quiz. To set it up, I want you to imagine that I have a mystery function, and I tell you that there's a certain secret number among all the numbers from 0 up to n-1, where if you plug that value into my function, it returns true, but if you were to plug in any other value, it returns false. And let's say you can't look at the innards of the function to learn anything about it. The only thing you're allowed to do with it is just try it out on numbers. The warm-up question is, how many times, on average, would you have to apply this mystery function in order to find the secret key? Well, if the setup was in an ordinary classical computer, there's really nothing better that you can do than guess and check. You go through all the numbers, and maybe you're lucky and find it early, maybe you're unlucky and it doesn't come up until later, but on average, with a list of n possibilities, it takes 1/2 of n attempts to find the key. Now, in computer science, people care about how runtimes scale. If you had a list 10 times as big, how much longer would it take? And computer scientists have a way of categorizing runtimes. They would call this one O of n, where that big O communicates that maybe there's some constants like the 1/2, or maybe some factors that grow slower than n, but the factor of n is what explains how quickly it scales as n grows. If n goes up by a factor of 10, the runtime also goes up by a factor of 10. Now, here's your quiz. For the equivalent of this setup, but in a quantum computer, what's the best runtime for finding the secret key? I've asked a variant of this quiz many times in a certain lecture that I've given over the years, and the options I typically offer are O of square root of n, O of log of n, O of log of n, and O of 1. The most common answer is always O of 1. And this is wrong, and I'm pretty sure that it stems from that misleading summary. That summary implies that you would put all of the n values that you need to search into this mysterious superposition, and then you would process them all in parallel, and then somehow the answer would be revealed. The second most common answer is typically O of log of n, and this is also wrong. You would call this an exponential speedup. For example, if you increase the size of the list by factors of 10, an O of log n runtime would only tick up by the same additive increment each time. Now, this wrong answer, I suspect, stems from a misconception about how much better quantum computers are in general. There are very certain special problems where you can achieve an exponential speedup. The most famous case is probably Shor's algorithm for factoring large numbers, but most problems are not like that. In this case, the correct answer is O of square root of n. And this is a lot more representative of the typical speedup that you could get with a quantum computer. In 1994, it was proven that a quantum computer could not possibly do any better than O of square root of n on this task. And then 2 years later, Love Grover found a specific procedure that actually achieves that runtime. So searching through a bag of 1,000,000 options takes on the order of 1,000 steps. A bag of 1,000,000,000,000 options takes on the order of 1,000,000. This big O actually hides something that's pretty fun, which is the constant of pi-fourths in the precise runtime, and that pi has its own whole fun story to tell, which I'll get to later. You might think that this puzzle with a mystery function triggered by one specific value is super contrived. But I want you to keep in mind this is meant to be a generic stand-in for any problem where you know how to quickly verify a solution, even if you don't know how to find that solution in the first place. This describes an enormous class of problems in computer science known as NP problems. So while a square root speedup is frankly not as earth-shattering as an exponential speedup would be, and while big O runtimes are often a lot less important than other practical considerations, it is thought-provoking that something like Grover's algorithm is even possible at all, providing this catch-all method for speeding up any NP problem. My goal with this lesson is to build up to a step-by-step walkthrough of how that algorithm works. It's actually very geometric and very beautiful.